Hello and welcome to a brief tutorial on crossover analysis. In this tutorial we'll also be talking about a special form of crossover analysis called break-even analysis. Crossover analysis is used to find the intersection of two lines. The easiest way to go about doing this is to put both of the lines in standard form where you have y equals mx plus b. Set the right hand side of each of the two equations equal to each other and solve for x. Once you have x, you can plug that x value back into either of the two original equations and solve for y. So we'll give you a quick illustration here. We'll actually have three lines that we're going to find crossover points for. Each line represents a different production process. Each line, as you see, has different variable costs and different fixed costs. So process A has the lowest fixed cost but the highest variable cost. C has the highest fixed cost but the lowest variable cost. So there's clearly going to be some trade-offs, and what we want to do is find the range over which each of these three processes would be preferred. So hopefully everybody remembers how to graph lines. The easiest way is just to pick 2 points. In this case, for Q, that's our quantity, and just plot those 2 points and then draw a straight line connecting them. So what we have here is we have the total cost, which is kind of like our y variable, equals the fixed cost plus the variable cost times the quantity. So I've just chosen two quantities. The first one, Q equals 0, which is generally the easiest one to do. So for what I'll do for the total cost of A, where Q is 0, I'll put 0 into this Q up here, and it will be 50,000 plus 8 times 0, which is 50,000, and that's represented here. So the total cost for C, then I'll put 0 in for Q on this bottom equation, and it will be 200,000 plus 5 times 5 times 0, 5.5 times 0, and our total cost will be 200,000. The next point, I just chose 100,000. It's a nice easy number to compute. So for A, I did 50,000 plus 8 times 100,000 is that 850,000. And then I did that same thing for the bottom two equations. So then if I'm going to plot these lines, again, I'm just going to plot the 2 points. You can see the 2 points for A here. The point 0, 50,000, and then the point 100,000, 850,000. Then I drew a line through those 2 points. I did the same things for B, the yellow line, and C, the green line. So because this is a sort of a business production problem, obviously our goal is to minimize cost. So we want to use the process that minimizes cost, and this is depicted by the process at any quantity that has the lowest total cost line. So for example, if our production volume we thought was going to be 20,000, here you see the total cost of the orange line, which is A, is the cheapest of the three, so that's the one we would select. B is next cheapest, and then C is the most expensive. We're all the way onto the right side of the graph where our production volumes are very high, say 100,000. Our order has switched. The lowest cost now is C due to its very small variable cost, and then B, and then A is our most expensive. So what we want to do is find the regions over which each of these lines is preferred. And you can see to the left of this arrow here, it looks like the orange line, so process A would be preferred. In between these two arrows, you see the yellow line is the lowest cost line, so over that range of volumes we would choose B. And then finally, to the right of the arrows with the very large volumes, the green line is clearly the lowest, so over those volumes we would choose C. So what we're going to do is for each of these two intersection points, the first one is where the yellow line and the orange line, that's processes A and B intersect. We're going to set those equal to each other and find the break-even quantity. And then the second one, just past the 60,000, is where the yellow and green lines intersect. So we'll find that intersection point as well. So all we're doing is trying to find the intersection points that are at the lowest, that affect our answer, the lowest cost. So we have A, B, and C would be our choices over those regions. So what we're going to do is we're going to set the two lines that cross equal to each other and solve for Q. So for the first one, we'll set total cost of A equal to total cost of B, and the total cost of A is represented by 50,000 plus 8Q, and the total cost of B is represented by 100,000 plus 7Q. Let's move all of the Q's to the left and all of the dollar amounts to the right, and we would see that our quantity equals 50,000. We need to do this for the total cost of line B and the total cost of line C because they intersected on that frontier. So substituting in the equations, moving all of the Q's to the left side, all of the numbers to the right, we would get Q equals 66,667. So let's go back to our graph. This is where we left off. Now what we can do is we can actually find the volume at which these intersection points take place. So for example, 50,000 is this intersection point, and then moving over we have 66,667. So this essentially gives us our decision rule. If our sales are projected to be less than 50,000, we should choose process A. If our sales are to be between 50,000 and 66,667, we would choose process B. And finally, if we had very high sales forecasted over 66,000, we would choose process C. A special form of crossover analysis is called break-even analysis. Here where instead of setting two total cost equations for two different processes equal to each other, we're going to use one process and we're going to set its total revenue equal to its total cost. And by definition, that's where profit is zero and the firm would break even. So let's assume a product sells for $50. The fixed cost associated with manufacturing this product is $100,000. That might be equipment or space that we have to rent or something like that. And the variable cost of production is $30 per unit. Generally that's stuff like direct labor and direct materials. We want to find at what quantity will the firm break even. So what we're going to do here, we have our total revenue equals 50 times dollars times the amount that we make. Our total cost is 100,000 plus $30 times the quantity we make. So we're going to set the total revenue equal to total cost. We'll move all of our Q's to the left and we would get an answer of Q equals 50,000. So this tells us if our volume is 50,000 or more, we'll make profit. If it's under 50,000, we'll lose money. So what does this look like graphically? Here you can kind of see I'm sketching the line, our total revenue line and our total cost line. And I just plotted those by choosing 2 points, just like we did in the first example, connecting the points and drawing the lines. So what you see at that 50,000 mark, the total revenue to the left of the 50,000 mark, the total revenue line, which is the yellow line, is underneath the total cost line. So that means our costs are higher than our revenues, so we have a loss. On the right hand side of the graph, we have our total costs underneath our total revenues, so our revenues were higher than costs, so we have a total profit.